NASA and its partners have taken to the air to help solve this elusive mystery. First, there's the Airborne Snow Observatory, or ASO, a small plane outfitted with a couple of instruments, one of which measures snow depth using LiDAR. LiDAR measures distance using light from lasers. Since 2014, ASO has flown over basins in California and Colorado, taking before and after looks at snow depth. Scientists subtract the snow-free summer data from the snow-on winter data to get an idea of the snow depth. There's no single way to measure all types of snow across the globe, and so NASA's other airborne campaign, SNOWX, is testing different combinations of sensors. This winter, SNOWX will test a new instrument, the Snow Water Equivalent Synthetic Aperture Radar and Radiometer, or SWISAR.
SWISAR consists of two main components, one of them being the radar and the second one being the radiometer.
So with the radar providing the depth of the snow and the radiometer providing the density of the snow, we could put those two things together and get the snow water equivalent. Here in the chamber, we're going to measure different radiation patterns at our different frequencies and do some full system testing in this chamber. This chamber kind of enables us to isolate various types of radiation and interference. And in about a month, we're going to take the instrument, mount it on a Twin Otter in the Grand Mesa in Colorado, and we're going to fly it over the Grand Mesa and take various different measurements. This is what we call our engineering flight.
Making sure the sensors are calibrated is key in order to face the challenges nature will throw at them.
Half of the area that gets covered by snow every winter contains trees and forest. And the trees make it difficult for the sensors to see the snow that's underneath the trees, so it makes it difficult for us to measure how much snow there is. After the snow's had a chance to sit on the ground for a while, it gets denser and denser and denser over time, and it changes, which is another reason why snow is very challenging to remotely sense. It doesn't stay the same. It's constantly changing. One of the things that we often do in the field is go dig what we call a snow pit. We literally dig a pit in the snow so we can see all the different layers. The layering is very important.
All this digging is part of ground truthing SNOWX, a way of matching up what the airborne instruments see and what is actually sitting on the surface. The ultimate goal of SNOWX is to figure out what the best combination of instruments would be for a future satellite mission in order to get
If the snow melts too fast, then you can get flooding. And if you don't have enough snow, or if the snow melts too early, that can lead to a longer wildfire season, a more intense drought, and we need to know these things for water resource planning.
I can't really name anyone that has so much integrity as she does to the things that she's accomplishing. It's pretty amazing. Having Claire as a role model, just a strong woman in science and just so smart and so kind. It's just a huge confidence booster. It's that, hey, I could do that too, you know? That's possible, that's successful, that's what I want to do.
I would characterize her as a pioneer in the field.
The amount and quality of the work she's put out is second to none.
I know people who have a lot of tenacity. I know people that have integrity, but it's rare that people have both together in that, that combination that Claire does.
Every morning, Dr. Claire Parkinson gets up before sunrise and runs 2 miles to work. She hasn't missed a day in nearly 40 years. To know the evolution of sea ice and how we observe it from space is to know Claire. This year, she's celebrating 40 years at NASA.
When I arrived at Goddard, which was in July of 1978, it was an incredibly exciting period here. Satellites were pretty new, but a lot of data had been collected.
NASA scientists were inundated with information, and Claire was in a cohort looking at sea ice, trying to make sense of a jumble of very raw, very new data. It was around that time that Claire and her team, at the time led by Dr. Jay Zwally, created the principal sea ice record that we use today. How does something like that record help you do your job?
Oh, that record is fundamental to understanding sea ice. So without it, we wouldn't know how rapidly it's changing.
You may not realize it, but Claire's work studying the changing extent of the ice caps deeply affected our understanding of climate change, and relatedly, our understanding of how climate change affects life on Earth.
One of the clearest signals for climate change that resonates with people has been this shrinking of the polar ice cap in the summer that we're able to see because of Claire's work.
After we had a record that was about 15, 20 years long, we started noticing that the extent of the ice in the Arctic was getting smaller over time.
Sea ice is formed on the surface of the ocean, and therefore is made from seawater. The biggest concentration is in the Arctic, and it's also where the biggest loss in sea ice is occurring. Every year, NASA reports on the sea ice minimum and maximum extents. As expected, the data is concerning.
By now, not only has this trend toward lesser ice continued, but it's even accelerated, so that now the decreases are greater than what they had been.
These trends are deeply troubling, but one thing's for sure. Our awareness of shrinking sea ice extent due to climate change was propelled faster and further after Claire Parkinson arrived at NASA.
I mean, she takes her job seriously, and the health and welfare of those instruments in space, yeah, she's on it. You know, it's one of the things you don't worry about because Claire's in the loop on these things. It's going to be fine.
In science, we stand on the shoulders of giants, on the shoulders of those who explored before us. But then, some among us are giants.
Tuesday was cold, I almost froze my toes. Oh, what's it gonna be next week? Who knows? That's climate. Oh, that's the climate you got. You take a bunch of weather and you average it together and you're doing the climate rock.
At a glacial pace, it means something's happening so slowly you can barely tell it's happening at all. That used to describe the very incremental movement glaciers and ice sheets experienced each year. But now that's changing. We're tagging along with 3 NASA scientists to understand the different lengths they go to not only investigate ice sheets and glaciers, but also communicate their often complicated science to the public. First, let's get oriented. Ice sheets, in pink, pretty much occur in only 2 places, Antarctica and Greenland. Glaciers, in yellow, play a key role draining melt off the ice sheet. Glaciers are also found in the high mountains, but we'll get to those in another episode.
So we know that something's happening in Greenland right now that's unprecedented in the last several thousand years.
That's Dr. Josh Willis, oceanographer at the Jet Propulsion Laboratory. Josh and his team are tackling one of the major environmental challenges of the 21st century, trying to answer fundamental questions about how melting glaciers impact sea level rise.
With my mission, Oceans Melting Greenland, or OMG for short, we're trying to understand just how much of Greenland's melt is caused by the oceans.
Along with being one of NASA's top scientists working on the cryosphere, Josh is passionate about demystifying climate change in typically unconventional ways.
I think by reaching out to people with a little bit of humor, a little bit of fun, maybe a song, you really have the opportunity to help people understand and come to terms with what we're doing to our planet. It's only a big deal, and we need to start preparing for it.
Down at the opposite pole, Dr. Kelly Brunt is getting ready for a major expedition.
In December and January this coming year, I'll actually be in Antarctica, down near the South Pole, collecting ground-based
Antarctica in a massive piston bully,